Hello. In this example, we want to talk about the properties of rational functions. Now, when we say a rational function, we're talking about a function that can be written in the form of p of x divided by q of x, where p and q are polynomial functions with the caveat that q of x is not equal to 0. Now, the reason that we say this is obvious because if you divide by 0, you get an undefined value. Now, the first thing we want to talk about is the domain. The domain of a rational function is all real numbers except for q of x equals 0. In other words, it's everything where q of x is not equal to 0. Now that's the domain. Here's the thing though. The places where the denominator is equal to 0 are in fact important. Those are what we call vertical asymptotes. Okay. So the solution to the equation where q of x equals 0, whatever solutions you get, it's going to be in the form of x equals a number. And when you graph x equals a number, that's just a vertical line. And a vertical asymptote, think of it this way. Think of it as a brick wall. The function cannot pass through the brick wall. It must be on both sides of it, but the function will never go through it. In other words, the function value, or the x value, will never be that number. Okay, now we want to talk about the horizontal asymptotes. A horizontal asymptote is effectively what the function is approaching as x gets really, really small and as x gets really, really large. Okay. So if we look at the horizontal asymptotes, you can think of this as the end behavior of the function. Now, if it's a horizontal, or if it approaches a horizontal line. Okay. One thing to keep in mind about horizontal asymptotes is the function can cross the horizontal asymptote. That doesn't mean that it will, it just means that it might. Now, to figure out what the horizontal asymptote is, or even if the function even has a horizontal asymptote, we need a couple of definitions. The first thing I'm going to do is I'm going to let n be the degree of the numerator. Then I'm going to let d be the degree of the denominator. There we go. There are three possibilities. If m is less than d, in other words, sorry, not m, n is less than d. If the numerator's degree is less than the denominator's degree, we have a horizontal asymptote, and that horizontal asymptote is specifically y equals 0. Now, when n equals d, we have a horizontal asymptote, and that's y equals the ratio of the leading coefficient of the numerator divided by the leading coefficient of the denominator. Okay, fantastic. And now the only other possibility that we have is that n is greater than d. In other words, the degree of the numerator is greater than the degree of the denominator. When this happens, there is not a horizontal asymptote. Technically, what it looks like is it's called an oblique asymptote. Now, the oblique asymptote could be, well, it could be a line that's not horizontal. It could be a quadratic. It could be a cubic. It could be any of those. But it's not horizontal. Therefore, there isn't one. Now, in 1314, we don't cover oblique asymptotes. In 1414, we do. So that's just one of the differences between the two types of classes. Okay, fantastic. So those are horizontal asymptotes. The next thing we want to do is I want to find, or I want to talk about x-intercepts and y-intercepts for a function. Now, for an x-intercept, you're going to set the numerator equal to 0. For the y-intercept, set all the x's equal to 0. Now, this isn't really anything new. You've actually seen this stuff before. For x-intercepts, you set the y equal to 0. But if you look at f of x, we defined as p of x divided by q of x. If I set that entire thing equal to 0, the denominator doesn't matter because the only way for something to equal 0 is for the numerator to be equal to 0. In other words, p of x has to equal 0, which is the reason why the numerator has to equal 0 for the x-intercept. Now for the y-intercept, the x is 0. And then you just simplify. And that'll give you the y. Fantastic. And there's one more thing we need to talk about, and the question becomes, does the function cross the horizontal asymptote? And here's how you test that. You're going to set f of x equal to the horizontal asymptote, or whatever number the horizontal asymptote happens to be. Now, if it's 0, you've already done this, because that's effectively looking for any x-intercepts. The other one is if it's a frankly, if there is no horizontal asymptote, there's no way for it to cross the horizontal asymptote, so don't worry about that. But if there is one where it's either 0 or a number, set the function equal to 0 and solve. Okay. And there you go. Well, that's pretty much everything you need to know about rational functions, or at least graphing rational functions. However, that's a lot of words. Just all this, lots of words. So what we're going to do instead now is we're going to actually look at some concrete examples, some actual functions. And it'll make things hopefully look a whole lot simpler, if not more clear. Alrighty, well, I will see you in the next video. Have fun.